This is a group of industrial manufacturing systems engineers from Iowa State University presenting on behalf of Syngenta in spring of 2018. Spring 2018's Syngenta group has not been the first to analyze the neighboring effect. In fall of 2017, direct neighbors were analyzed to see if they caused an effect on the subject plant. These neighbors are pictured on the right-hand side of the screen in yellow. When looking at which hybrids move forward, there are two types of errors, false positives and false negatives. To further investigate the impact that neighbors can have on these errors, spring of 2018 has looked into diagonal neighbors, pictured in purple. When calculating residuals for the nearest direct neighbors, yield to true yield difference and average neighbor yield difference were the only two models used. Residuals used for the diagonal neighbors not only included this, but also compared these residuals to the diagonal neighbor yield difference. This will show the diagonal neighbor influence, where data will then be combined by location to show the root mean square error. From data collection, the yield of each hybrid is considered to be the primary selection factor to move forward. The higher a hybrid yield is, the more likely it is to be selected. There are no buffer plants surrounding the plots planted, meaning that plants on the outside of each plot have no protection from the elements. The yield each hybrid has in plot C is considered to be the true yield for that hybrid. Along with the lack of physical access to the plots, missing data points, and operator error, we were given few replications in selective data.
There are some important topics around environmental, worker, and stakeholder impact that should be addressed. Syngenta must follow the Global Reporting Initiative, which has legislation around labor practices, human rights, and environmental regulations. The company also has something called the Good Growth Plan, a broad goal for a brighter future, where new hybrids can produce more food in worsening conditions, lowering the price and helping the impoverished. The impact made by our new neighboring effect adjustment model provides better stage-by-stage data, improving the selection process. Hopefully this will help Syngenta on their goal to feed the world. Some of the standards surrounding this process are a regression analysis to compare new data with old data using p-values as a metric, a covariance analysis which gives variance inflation factors by location for hybrid yields, and a ANOVA/Papadakis model to quantify the neighboring effect adjustment model, which provides more accurate yield values. Technologies with the project are RStudio, Excel, and Jump to organize the data and calculate linear regressions, the extent of the neighboring effect, and a new adjustment model for the company. There is a lot of room for economic opportunity in the hybrid selection process. Currently, there is a projected advancement error of 25 to 40%, which is costing the company about $400,000 every 3 years. This error has the potential to increase profit when reduced.
Okay, so I will talk about what analysis we are doing for the whole project. The first thing is the formulation of the NIAM model. NIAM stands for Neighboring Effect Adjustment Model. It's a model that will help us removing the neighboring effect from each hybrid. The first thing that we do is to find the best model to predict the neighboring effect. There are 4 basic models that we use to quantify the neighboring effect. After we find the best model, we will use that model to formulate NIAM model. This is the 4 basic models that we need to compare and find the best one. The first one only consider the direct neighbor, the second one only consider the diagonal neighbor, the third one consider the average of both direct and diagonal neighbor, and the last one consider both direct and diagonal neighbor as a standalone variable. These are the results for the regression analysis of the 4 models. What we want is a model with the least amount of RMSE and the most R-square value. As we can see, the last model has the least amount of RMSE and the highest R-square. So we will take that as our best model. We also created a regression analysis for each location instead of the whole group. This can be used as a backup model if Syngenta thinks that the model with the whole group isn't accurate enough.
At this point, we selected a previously mentioned equation to form our new model. In order to select this equation, we looked at the regression analysis for each equation. The value that we were most interested in at this point was the RMSE, or root mean square error. In this case, the lower the RMSE, the lower the error rate. Then we analyzed the regressions based on location and hybrid group in order to find the best possible model. Based on our regression analysis, this equation led to the most valid model and was used to create the model. Using this model can help us find the predicted final yield of the test hybrid. This equation for the predicted model is the actual yield minus the YTM SYD. At the bottom is our final NIAM model, or the neighbor effect adjustment model. The values for the intercept and the slope came from our regression analysis of the 2 hybrid groups. Here's a comparison between the observed YTM SYD and the predicted YTM SYD. The observed histogram is the result of the NIAM model using only the A and YD. Our predicted histogram is the result of the NEAM model that we created. As you can see, moving from the observed to the predicted, the YTM-SYD becomes more centered around 0. This equates to fewer hybrids incorrectly chosen to proceed to the next stage of testing, ultimately reducing type 1 errors. Following these steps will allow Syngenta to streamline their testing and save money in the process.